Have you ever wondered how systems transition from one state to another? Welcome to the fascinating world of state transition diagrams. These diagrams, also known as state machine diagrams or Statechart diagrams, are used to illustrate the dynamic behavior of a system or entity. Imagine a traffic light that changes from red to green, or a vending machine dispensing your favorite snack. How do these systems know when and how to change their state? The answer lies in state transition diagrams. These diagrams are composed of four key components: states, transitions, events, and actions. States represent the conditions or situations in which a system exists. Transitions illustrate the change of state triggered by an event or condition. Events are the signals or occurrences that trigger these transitions. And actions, they're the behaviors or operations performed when a transition occurs. By the end of this video, you'll have a solid understanding of how state transition diagrams work and how to use them in your own projects. Let's dive in with our first component, states. Picture it like this. A state is like a snapshot of your system at any given moment. It's like a photo capturing a specific condition or situation in which the system exists. In the realm of software development, this could be anything from a user having logged in to a file being open, or even an error being encountered. A state is not just limited to software development, it's a universal concept. Think of a light switch. It has two states, on and off. Or consider a traffic light, cycling through red, yellow, and green. Each color represents a different state. In a state transition diagram, states are depicted as rounded rectangles. Inside these rectangles, you'll find labels describing the state. So in our traffic light example, you'd have three rectangles, each labeled red, yellow, and green. It's also important to note that a system or object can have multiple states, but it can only be in one state at a time. For instance, a traffic light can't be red and green simultaneously. That would cause chaos. But states don't exist in isolation. They are part of a larger system that reacts to events or stimuli. This is where transitions come into play, but we'll discuss those in more detail in the next scene. One more thing to note about states is that they are dynamic. They can change over time in response to events, user actions, or other stimuli. This dynamic nature is what makes state transition diagrams so powerful. They provide a visual representation of how a system behaves over time. So, to sum it all up, a state describes a specific condition or situation in which a system can exist. It's a snapshot, a moment frozen in time, representing the system at that specific point. And the entire life cycle of a system can be traced through these states, from the initial state to the final state, with many potentially complex states in between. So a state describes a specific condition or situation in which a system can exist. But how does a system move from one state to another? That's where transitions come in. Transitions, as the name implies, are like bridges that connect states in a state transition diagram. They represent the dynamic aspect of the system, the shift that occurs when a system or object moves from one state to another. Each transition is typically depicted as an arrow pointing from the initial state to the final state. Think of it as a roadmap, with states as destinations and transitions as the routes that take you from one destination to another. Now, what makes a system decide to pack its bags and move to another state? That's where events enter the picture. An event is a trigger, a signal that spurs a system into action, prompting it to transition from one state to another. Events can be like a tap on the shoulder, a nudge to remind the system that it's time to change states. Events can be external or internal. An external event might be a user input or a change in the environment that the system responds to. For instance, in a coffee machine, the press of a button might trigger the transition from a standby state to a brewing state. On the other hand, internal events are generated within the system itself. To continue with our coffee machine example, the completion of the brewing process might trigger an internal event leading the system to transition from the brewing state back to the standby state. Transitions and events are two sides of the same coin. Transitions define the path, and events provide the push. They work hand in hand to illustrate the dynamic behavior of a system. But it's not just about moving from point A to point B. Each transition can also be associated with actions, behaviors that the system performs when it makes the leap from one state to another. For instance, in our coffee machine, the action associated with the transition from standby to brewing might be the activation of the heating element. Transitions then represent the changes that occur in response to events. So, whether it's a traffic light switching colors or a coffee machine brewing your morning cup, it's all about transitions and the events that trigger them. So we've got states and we've got transitions, but what happens when a transition occurs? In the exciting world of state transition diagrams, the transition isn't just about hopping from one state to the next. No, it's much more than that. It's about what happens during that journey, that leap from one condition to another. And this, my friends, is where actions come into play. In the context of a state transition diagram, an action is a behavior or operation that is performed when a transition occurs. It's the doing part of the process. The action is the response to the stimulus or event that triggers the transition. It's the system's way of saying, okay, I've received this signal, and now here's what I'm going to do about it. Now, actions are not just random responses. They are purposeful, tied directly to the transition they are associated with. Think of them as the instructions or the commands the system follows when moving from one state to another. They specify the behavior that occurs during the transition, guiding the system on its journey from the current state to the next. So, let's take an example. Consider a simple coffee machine. When you press the start button, that's an event. It triggers a transition from the idle state to the brewing state. But what happens during that transition? That's right, an action occurs. The machine starts brewing your coffee. Now, it's important to note that actions are not always immediate. Sometimes they might involve a series of steps or processes that the system undertakes. In our coffee machine example, the action could involve heating the water, grinding the beans, and then brewing the coffee. Each of these steps is part of the action that occurs during the transition. And there you have it. Actions are the dynamic responses that occur during transitions, giving life and movement to our state transition diagrams. They are the nuts and bolts that make the machinery of our systems work, the heart that keeps the rhythm of our processes alive. Actions, then, define the behavior or operation that is performed when a transition occurs. Now that we've covered the basics, let's look at some more advanced concepts in state transition diagrams. First up, the initial state. This is the starting point in the life cycle of an object or system. Think of it as the on button, the moment when the system springs to life. It's represented by an arrow with no incoming transitions, paving the way for the journey through the states. Next, we have the final state. This is the end point of an object or system's life cycle. It's the off switch, the moment when the system's operation terminates. A solid circle denotes the final state, signaling the end of the road. Moving on, let's talk about guard conditions. These are Boolean expressions that must be true for a transition to occur. They're like gatekeepers, ensuring that certain criteria are met before allowing a state transition. This adds an extra layer of control, enabling us to specify additional conditions for transitions. Last but not least, we have the composite state. This represents a hierarchical state that contains nested states and transitions. It's like a state within a state, allowing us to model complex behavior and states within a system. This comes in handy when dealing with intricate systems where states have their own substates and transitions. By using these advanced concepts, we can create more detailed and nuanced state transition diagrams. We can capture the dynamic behavior of systems more accurately, even when they are complex and multifaceted. So whether it's a traffic light cycling through red, yellow, and green, or a software application transitioning between different operational modes, these advanced concepts provide the tools to model and understand these systems better. Remember, state transition diagrams are not just diagrams. They are powerful tools that provide a visual representation of how a system behaves, helping us design, develop, and troubleshoot more effectively. These advanced concepts allow for more complex and nuanced modeling of system behavior. Now, let's apply what we've learned with an example. Picture this, a traffic light system. It's a classic scenario, simple yet effective for illustrating the concept of a state transition diagram. In our system, we have 3 states, red, yellow, and green. Each state represents the color displayed by the traffic light. The transitions, they're triggered by timer expiration, the event in this case. So we start in the red state. When the timer expires, the system transitions to the green state. This is the action taken in response to the event. After a certain period, the timer expires again, prompting another transition, this time from green to yellow. Finally, another timer expiration takes us from yellow back to red. And voila! The cycle continues, indefinitely switching between states in response to the timer expiration event. And there you have it, a simple but effective example of a state transition diagram in action.